Your local model can be fast on the first token and still crawl after that. I'll wire up vLLM Speculative Decoding so you can actually cut generation latency instead of just changing prompts. This is the setup you'll be able to run after this, which chooses speculative decoding for a prompt and reports latency and speed up. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Latency spikes show up in real projects all the time. A request starts fast, and then the decoder waits on each token. That hurts chat responsiveness and increases cost when you run models locally. vLLM Speculative Decoding is a server-side trick that lets a smaller helper model propose tokens, so the main model does fewer slow steps. Success looks like noticeably faster tokens per second, without a hit to output quality. We will build a small experiment that measures a baseline, enables speculation, tunes a depth knob, and then uses those measurements to decide when speculation actually helps. Conceptually, think of two decoders. One is slow but accurate. The other is light and guesses ahead. The light decoder proposes a short draft of tokens, and the slow decoder only checks or corrects as needed. If most proposals are accepted, you save time. If many are rejected, you waste effort. This method shines when you need many tokens per response. We will set up 3 short measurements and 1 tuning test, then make a simple decision rule that chooses speculation only when it yields savings. The code is small, and the timing numbers give you a clear trade-off before you flip the switch in production. Now we run a first deterministic baseline to measure a minimal per request cost. This snippet sends a deterministic baseline chat completion to a local vLLM server. It points the OpenAI-style client at the vLLM base URL, so requests hit your local model. The variable model names the main model, and prompt provides a concise task to generate stable output. The client chat completions create call sends messages with temperature set to 0 and a small max tokens to keep this inexpensive and repeatable. The response R1 includes usage, where completion tokens reports how many tokens were generated by vLLM. The printed token count establishes a minimal baseline you will try to improve with speculative decoding. Next, we extend the baseline to measure steady throughput over a longer generation. This example times a longer baseline completion to measure throughput from the local vLLM server. It starts a timer and calls the same client chat completions create call with the same model and prompt, but requests more max tokens to get a steadier reading. After the call returns the code, captures elapsed seconds as DT. The variable base TPS divides completion tokens from R2 usage by DT to compute tokens per second. That metric emphasizes inter-token latency more than simple wall clock for the request. Increasing max tokens enlarges the sample and stabilizes the metric, while decreasing it makes measurements cheaper but noisier. The printed baseline TPS quantifies your current serving speed. Now we enable the draft model, so the server uses speculative decoding and compare speeds. This code enables vLLM Speculative Decoding by adding a smaller draft model in extra body, and then measures its effect. The variable draft names the lightweight helper model vLLM uses to propose multiple tokens per decoding step. The client chat completions create call is otherwise identical to the baseline, but includes extra body with the draft model name, which activates speculation on the server. After timing the request, the code reads RS usage completion tokens and computes STPS as tokens per second. The ratio against base TPS yields speculative speedup, which shows how much faster the combined draft plus target process is. Larger prompts and longer generations usually benefit more, while very short outputs may see limited gains. The printed speedup confirms whether speculation helps on your hardware. Next, we tune how many speculative tokens the draft model proposes each step. This snippet tunes vLLM Speculative Decoding by setting num speculative tokens to increase the draft model proposal depth. The client chat completions create call still uses the same model and prompt, but adds extra body with both draft model and the tuning parameter. After timing the request, the script records RT usage completion tokens and computes tuned TPS as the realized tokens per second. Increasing num speculative tokens often improves throughput because the draft amortizes more of the target model cost. But pushing it too high wastes proposals that the heavy model later rejects and can reduce effective throughput or quality. Lower values are safer on small GPUs, while higher values can shine on larger cards. The printed tuned TPS reveals whether deeper speculation improved decoding speed. Finally, we apply the measured throughputs to a routing decision for longer responses. This example uses measured vLLM throughputs to make a simple incident-style decision for longer outputs. The variable target tokens represents an expected response length you care about in production. The code estimates baseline and speculative latencies by dividing target tokens by base TPS and tune TPS gathered from earlier calls. The best variable selects the faster mode, and saved computes the potential time reduction in milliseconds. You can lift target tokens for verbose answers or lower it for short replies, and the crossover point helps you route requests intelligently. The printed decision and estimated savings make the trade-off visible, so you can enable speculation only when it pays off. In short, what you built is measurable speculative decoding for vLLM. Use it when your responses need many tokens and inter-token latency dominates. Expect speedups when a small draft model makes accurate proposals. One caveat is that too aggressive speculation can waste compute or harm quality if many proposals are rejected. A clear next step is to sweep num speculative tokens and the draft model choice to find the sweet spot for your GPU and workload. That tuning will show the real crossover point where speculation consistently saves latency. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.